If you're trying to evaluate a limit, of course, the first thing you always want to try is direct substitution. If you get a numeric value through that method, then great, you're done, you found your limit. If you don't get a numeric value, if you get something maybe like 0 over 0, try something else, like factoring. So here's an example. We have the limit as x approaches 3 of x squared minus 9 over x minus 3. And if you do direct substitution with that, if you plug 3 in everywhere there's an x, of course, you're going to see that both the numerator and the denominator go to 0. We consider that an indeterminate or indetermination. Basically, if you get 0 over 0, that tells us nothing. We don't know if that limit exists or doesn't exist. We have to take more steps. So 0 over 0 tells us nothing. So what we can do is play around with the limit. Let's see if we can factor it. So here, the limit, and again, we always rewrite that limit statement until we actually have reached a limit. So the limit of x squared minus 9 over x minus 3 is equivalent to the limit of x plus 3 times x minus 3 over x minus 3. I just factored that numerator. It's a difference of squares, pretty simple factorization. Now, we know that x equals 3 makes that denominator go to 0. So what that tells us is, because you're not allowed to divide by 0, that function is undefined at x equals 3. That means when you graph that function, and you actually see here I have a little sketch of the graph, when you graph that function, when x is equal to 3, there's a hole there because the function is undefined there. But since the denominator cancels away, meaning since that we can take the x minus 3 over x minus 3 and consider that equal to 1, this limit is equivalent to, and I'll just show sort of canceling that away, this limit is equivalent to x plus 3. Okay, so the graph actually looks just like x plus 3. It's just that since we're undefined at x equals 3, we have a hole there. Now that's because that denominator cancels away and we no longer have 0 in the denominator. So with all that said, we had our original limit that we were investigating. We tried direct substitution. We got 0 over 0, which told us nothing. We went ahead and factored and reduced, and we ended up with a simplified limit. Now we can try direct substitution again, plug in 3 where there's an x, and of course now we get 3 plus 3, which equals 6. So our limit is in fact equal to 6. So looking at the function graphically, we know that f of x is defined for all x values except at x equals 3. And after investigating the limit as we approach x equals 3, we know that the graph actually also resembles y equals x plus 3. So here we have a linear function, x plus 3, that clearly has a hole in it when x is equal to 3. And our limit from the left and our limit from the right, as x gets closer and closer to the 3, the limit from the left and the limit from the right are both heading the same place. They are both heading towards 6, the y value of 6. So we do know that the limit of this function, we've seen it now graphically and algebraically, we know that the limit of this function as x approaches 3 is 6. So as x gets closer and closer to 3 from each side, f of x gets closer and closer to 6. It does not matter that there's a hole there. The point doesn't have to exist. We just have to have the graph heading there. Now I have some notation here. The limit from the left, of course, I went ahead and reduced the limit to x plus 3. If you imagine a value just below 3, remember it's 3 minus, so something like 2.999. We take that for our x value, 2.999 plus 3, that is 5.999. So the limit as x is getting really close to 3 from the left, the closer and closer we get to 3, 2.9999999. Our limit is going to approach 5.99999. All said and done, that means that limit is approaching 6. Likewise, as we come in from the positive side, something just above 3, 3.00001, for instance. We plug that in for x, and our limit is going to then be 6.00001. So from the right-hand side, we are also, the closer the x value gets to 3 from the positive side, the closer the output value gets to 6. And again, since my left-hand limit was 6 and my right-hand limit was 6, that means they agree, they're the same numeric value. That means my two-sided limit is also 6. Remember, a two-sided limit exists if the limit from the left and the limit from the right approach the same numeric value. 6 is definitely a numeric value. Remember, infinity would be something that's not a numeric value. And just as I've mentioned in previous videos, IFF is not a typo, it means if and only if. So the two-sided limit exists if and only if the left-hand limit and the right-hand limit equal the same numeric value. And going in the other direction, the left-hand limit and the right-hand limit can only be equal if and only if the two-sided limit exists. Let's take a look at another example. This one is the limit as x approaches -4 of x cubed plus 64 over x plus 4. Now, if we do our direct substitution, what we'll find is, of course, I'm putting in -4 everywhere that there's an x. -4 cubed gives me -64. And what you notice is we get 0 over 0. Once again, 0 over 0 is an indeterminate, and that means we know nothing. We have to try something else. 0 over 0, we could end up with a limit that does exist. We could end up with a limit that doesn't exist. We have to try further steps. So I happen to recognize that 64 is 4 cubed. So the numerator is a sum of cubes, and I know how to factor that. If you don't remember, there is a formula for both the sum of cubes and the difference of cubes, and they're good to have on hand. So I'm going to rewrite this limit as x approaches -4, and the factorization of this is x plus 4, and then x squared minus 4x plus 16. And on the bottom we have x plus 4. Now, what you'll notice is I have x plus 4 in both the numerator and the denominator. So in a sense, those guys cancel out, and what we're left with is an equivalent limit, which is x squared minus 4x plus 16. Now we can try our direct substitution. And when we plug in -4, we end up with -4 squared minus 4 times -4 plus 16. And this is positive 16 plus 16 plus another 16, which gives us a grand total of 48. So even though we got 0 over 0 to begin with, it turns out that the limit of this function does in fact equal 48. We know that -4 makes that denominator in the original function go to 0, which means our function is undefined at that value x equals -4. Again, just like the previous example, since that denominator cancels away, we know that x equals -4 tells us we have a hole there. The function is not defined there, but the limit does exist. And it turns out, you notice after we did all of our reducing, we ended up with a quadratic here. And in fact, that is the shape of this graph. So what we end up with after factoring is what the shape of the graph is. This is going to be a parabola. And this original denominator tells us that it's undefined at -4. And the graph looks something like this. We've got a hole, and then we have a parabolic curve. Again, just a sketch, but this hole here would be at -4, 48. The function is undefined there, but the limit from each side is approaching 48, so that limit does in fact exist.